All right, good afternoon. Since we're up against lunch here, I thought I'd start with my summary slide while I have your attention. So we've identified in this meeting that Seafloor geodesy is needed to help resolve a lot of the questions we have for the major questions we have regarding subduction zones. I'm going to present some results for Cascadia using GNSS velocities and that data. And basically what we see is that those velocities are tracking the incoming plate, the Wanafuka plate, indicating that Cascadia is mostly locked, or central Cascadia is mostly locked up to the trench. But this lock zone is particularly narrow on this part of the subduction zone. I'm also going to talk about a C4 geodetic community experiment that a group of us are starting to launch. This will establish a backbone GNSS acoustic network in Cascadia, Alaska. It's going to provide an opportunity to streamline a lot of our operations and think about how to upscale a lot of these activities. And it will be an opportunity to really grow the research community and the number of people that are utilizing C4 geodetic data. Additionally, I wanted to talk about some considerations thinking about implementation of SZ4D in the marine environment. One thing to keep in mind is that it's important to use mature technologies once you upscale to a large array. There's a lot of advantages being on the seafloor versus on the land. We don't have to worry about water loading or groundwater issues, but it's also a very hostile environment. It's remote, it's cold, it's corrosive to instruments, and it's under pressure. And for all those reasons, it's not kind to instrumentation. So we do need to scale up the mature technologies, but we also have to have an eye towards emerging technologies and provide platforms to test those emerging technologies. Thinking about the operational aspects of a mega array, it will likely need to be a phased development plan, a phased deployment plan of actually putting instruments out. Just getting all the equipment ordered from the manufacturers will take a couple of years to get all those instruments produced. So that needs to be factored into that planning. Multiple types of observations will be needed because we need that to help resolve the non-uniqueness of the problem. Particularly for GNSS acoustic, we need to be patient with those. It takes time to build that data set up, those time series. So we might consider dropping those benchmarks in the ocean, getting some initial surveys early so that those data become mature when the other geophysical data become available to us. And finally, the variations in acoustic velocity in the water column is our largest source of error. So we should be thinking about engaging the oceanographic community in both the experimental design and the data analysis. So on to some details here. We've talked about the motivating questions, and Seafloor geodesy has a role to the three, which somehow they all turn to ones for the SU motivating questions. But Seafloor geodesy has a role in looking at the interaction of the faults in space and time, identifying the speed and mode of slip in space and time on these structures, and particularly looking for precursory slip that might be happening, or are there distinctive activity on these subduction zones. So how do we make these observations for seafloor geodesy? There's a range of instruments that we have in our toolkit. These are mostly mature technologies, although some are still in development. For horizontal deformation, GNSS acoustic and direct path acoustic are the two mature technologies. Fiber optic strain is something that is currently in development. For measuring vertical deformation, we utilize seafloor pressure, as well as gravity tilt and differential bathymetry. And then we can also use formation strain, changes in strain related to the volume from corks or looking at fluid flow. Okay, so I'm going to focus on GNSS acoustic. This was a method first developed by Fred Spiess and then refined by Dave Chadwell over the past couple of decades. And it's a method to really measure the horizontal position on the seafloor down to about centimeter precision. And it puts those positions in a global reference frame. And that's really critical to any kind of geodetic technique, is having a measurement that you can tie into the data set that you have on land. We do this by putting down an array of transponders on the seafloor. And so in this picture, we see some transponders on the back deck. They're sitting on a cement benchmark. Basically inside those orange hats is a glass sphere. And at the top of that orange hat is the actual transponder that talks acoustically. We collect the data by sending out a wave glider, and we'll see if the video is going to play. It looks like it's going to stall out and not play, but you can see there, we'll start from the back there. You can see the wave glider dangling from the crane there. It's still not going to play. So basically the wave glider, it's a remotely operated surface vehicle. It allows us to collect the data from steering and operating the payload from on shore. It's basically a large surfboard. It has a solar panel array and the GPS antennas. And we use that surface platform to collect the GNSS data from the satellites. At the same time, we're acoustically talking with the transponders on the seafloor. That wave glider, it operates on its own under our direction, and it's propelled by wave action with a glider system that's hanging down underneath the craft. The system is set up such that the transponders on the seafloor can be recalled once their batteries expire. The orange hats release from the Schmidt benchmarks. We collect them at the surface, swap out the batteries, and then take an ROV down to put the transponder back onto the benchmark and continue the time series. So this ensures that we have a stable benchmark that we can continue to survey for decades into the future. So let's look at some of the results in Central Cascadia. We've been running this experiment off of the coast of Oregon, 4 sites on the accretionary prism. We also have a legacy site that Dave Chadwell first collected data at on the incoming plate. That would be JNP1. So we've been conducting yearly surveys, except for a hiatus over COVID, since that interfered with a lot of our field operations. We've retrieved and swapped out the batteries at most of these sites. So we've refreshed the batteries, put them back on the benchmark, and continue to collect data. And so we've demonstrated that we can extend these time series into the future. So generally you see that for the southern 3 sites in the accretionary prism, they're tracking with the incoming Juan de Fuca plate. The azimuth agrees quite well, which gives us some confidence that we're actually making good measurements here. The site to the north, NGH1, that has the least amount of data currently. And so you can see its azimuth isn't quite right. Generally, you need about 4 to 5 surveys before you can really feel confident in the result. And here I'm showing 2 time series where for 2 of those sites, the 2 central sites for the north component. And the error bars, the error ellipse that you see represent the ability to fit a line through those data. And again, our largest source of error is the oceanographic artifacts. Okay, so I have some preliminary modeling results to show with the data. I'm going to focus on the data in Newport at NNP1. So this is in a profile in Central Oregon. I'm going to use a backslip elastic half space model to give a first order estimate of what we might be looking at. And so basically what I've done is I have a simple slip rate deficit function. They're kind of depicted on the right side of the screen here. And I do just a straightforward grid search of modulating that slip deficit rate function, perturbing all the parameters to see what range of models could possibly fit the data. I also, with this, I'm using a boundary element code where I can allow for stress shielding up at the trench. So in other words, I can assign a stress-free boundary condition on some of those fault elements and allow for a lock zone to be down dip and just let that upper part slip however it wants. So this can accommodate the stress shielding scenario. So obviously this is a non-unique problem. There's a whole range of models that potentially fit the data. I'm going to focus on 3 classes of model that all fit the data equally, model A, B, and C. The model B there in the middle is just if we had 100% locking, what would the down dip locking look like? You can see you get this narrow zone. Model C is if we start lowering the locking threshold, what we get. You can see the locking zone tends to widen. And then model A at the top is that scenario of, what if you had a freely slipping little patch up near the top, what would you accommodate? And then the lock zone narrows even more. We can draw profiles. So for each of those 3 models, there's the model prediction along an east-west profile. The data is shown there on the far right. The little tiny error bars are the velocities that we see on land. You can see small error bars. NNP1 is that Newport site on the accretionary prism, and then we have the JMP site, which is on the incoming plate. So these 3 classes of model all go through that NNP1 site within uncertainty. There is the potential for a small amount of creep up near the deformation front, but it'd have to be under 5 millimeters per year in order to fit that NNP1 site. Okay, so this is kind of a cartoon summary. If we take that here, I've drawn a profile through the bathymetry and topography in Oregon. We have the deformation front there on the left of the plot, all the way to the coastline, the Coast Range, and then the Willamette Valley. And then I have those three models, which I've just made a cartoon of how the locking state might vary along the dip. So all of these models basically push a lock zone out near the trench by various degrees. You have a broad transition zone that exists beneath the shelf, and then the ETS zone would sit down to the east. In that transition zone, that's where we would have partial locking. So that means that there's active slip, presumably happening, aseismic slip happening on the megathrust. And this would also be the zone where, when we have an ETS event, you're sending stress waves up to the bottom portion of the lock zone. So you could have modulation. This is part of one of the goals of SZ4D, right, is to look at potentially precursory slip. This is where you would expect to see that stress erosion over time based on dynamic models. I mentioned that some of the models allow for some creep near the deformation front, but it would need to be small. So all of these models predict a very narrow lock zone off of Central Oregon. And just for comparison, here's a similar profile off Nankai, looking from the deformation front on the left, all the way to the island of Shikoku on the far right. And you can see the coastline there. And there's an excellent GNSS acoustic data set in Japan in this area. And from the models that come from those data, you can see they predict a very broad lock zone beneath the shelf. And if you compare that to Cascadia, it just puts it in perspective that the lock zone is very narrow for that central Cascadia part. Just a quick plug, William Wilcock will have a poster, and I think also a lightning talk, just emphasizing that the central part of the Cascadia arc is an opportunity. The OI cable is underutilized. It has a very small geophysical footprint there, and it would be a great place to both test instrumentation and to get our high rate continuous data that we so much crave. So the other important thing I wanted to bring up was this C4 geodetic community experiment that's taking place. We're just starting to launch this. It was just funded by NSF this past summer. This is a culmination of 2 virtual workshops that we've had over the past couple of years through the pandemic to bring the community together and to plan out how we wanted to utilize this C4 geodetic instrument pool that we have available to us. This will be a 5-year community experiment. The community in those workshops decided that we would split enough instruments for 12 sites between Cascadia and Alaska, 6 in Cascadia, 6 in Alaska. On the on the maps there's the small white triangles, which might be hard to see. Those are places where we have existing GNSS acoustic data. The University of Victoria group has their array up off Vancouver Island. The USGS has 2 sites in Southern Cascadia, and then we have our current experiment in Central Park of Cascadia. The yellow triangles are sites that we deployed this past summer that are part of the community experiment. We'll deploy the red sites in Cascadia this coming summer, and then in 2024, we'll deploy the Alaska sites. All of these sites will include an absolute pressure gauge as part of the array. In addition to the actual data collection that will take place, since this is a community experiment, we'll have an open data policy. We'll be working with the UNAVCO consortium to develop a Seafloor geodetic data archive to disseminate that data and also to disseminate both low-level and higher-level products. We'll be developing an open source processing package to process GNSS acoustic data. And this is really to enable the community to take advantage of those data, the terrestrial geodetic community to start to have access to Seafloor geodetic data. There'll be an apply to sell program with this, as well as a series of training workshops. In addition to just the scientific goals of collecting this data, one of our other big objectives here is to enlarge the Seafloor geodetic community. And so bringing people on board, particularly young investigators, is really an important part of the mission here. Okay, that brings me back to the summary slide here. And I'll just, I already went through them. I'll just let you read it and I'll stop there.